Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future. So today we are going to continue on a practical part. It's actually fun because we can play around with PostgreSQL. Who of you actually already tried the Docker and made it work? Some of you, very good. Who hasn't yet? Yeah, that's okay. You can try it and tell us if you have any issue with this. Just so you know, there was an initial notebook for the test of PostgreSQL that had an extra line that wasn't supposed to be here, but that had been fixed. So if you got an error, you just need to use the new notebook that is right now in the Moodle, the one that's called the test installation PostgreSQL or something like this. All right, let's get started then. What is a relational table? Anybody? Mathematically? Yes? Mm-hmm. Mm-hmm. Yes, absolutely. So a table associates values to headers. So we call these headers attributes. And mathematically, so what you've just expressed, it's a set of maps, right? So the automatic answer that you can have when I say what's a table is it's a set of maps, right? But what you said is exactly the explanation of a set of maps. So indeed, the maps associates values with attributes, every map, and then we have a set of them. Do you remember once we say that it's a set of maps, there's 3 additional constraints. Do you remember them? Integrity constraints? Yes? Exactly. Relational integrity, atomic integrity, domain integrity, right? Relational integrity tells us all the maps have the same supports. So they have the same attributes. That's why you have the attributes for the entire table. The atomic integrity means that there is no table in the table in the table in the table. So you just have atomic values in there. We'll see today the atomic values. Domain integrity means in the same column, you must have values of the same type, right? Who is with me on this? Right? Very good. So that was the theory. And now we are going to define what these attributes are for a table and define what these domains are for the table. This is what we are going to do right now. So the name for a domain actually is a type. Every domain has a type, and the values in the column associated with this domain have that type. So I'm going to drive you through this, give you plenty of practical example with PostgreSQL. So I left you with the fact that you have schemas in a relational table that have the attributes, their associated domains like here and here, and then the primary key that will be in a couple of weeks. But today I want to go in these, like what is string, integer, what can we put in there basically? What domains can we have? And so there's plenty of them, and I'm going to go through them. Let's start with strings. So now I'm just careful because for computer scientists, it's obvious. Who knows here what a string is? Who doesn't know? So almost all of you, all right. So a string is just a sequence of characters. It's basically text. You can think of that as text, right? So what you need to know is that the strings in programming languages, we typically quote them with double quotes or single quotes. In PostgreSQL, it's single quotes. If you try to use double quotes with strings, it's not going to work. The double quotes are for the attributes, and the single quotes are for the string that you put inside the table, right? So this is why I put these single quotes right here. And as I said, technically, what it is, mathematically, it's a sequence of characters, right? So that's FOO, that's ZURICH, Isabelle Zalstenar, that's a famous opening for a novel. So this is a sequence of characters like this, okay? Now, what does that mean in PostgreSQL? How can we have attributes, columns that use this? Well, there are several ways to do that. The first thing that you can do is you can define a type for a column that has a fixed length, specified number of characters. It makes sense, for example, if you have a table on Switzerland and you want to use the codes for the cantons, you know it's 2 letters for every canton. And so then you could say, I want a fixed length of exactly 2 characters in my string for this column, right? And then that could be used for contents. Or you could say, we have some elasticity. It can be different lengths, but with a maximum. For example, you could have for license plates, for the country on the license plate, you know, what the sticker you put on your car, it has 1, 2, or 3 letters. So then you could say it's a variable length with a limit of 3, right? 1 is fine, 2 is fine, 3 is fine, right? Even empty would be fine, all right? So this is the second thing you can do. And just give me a second to add you as a co-host. Make sure. Marcin, right here. There you go. All right. So finally, what you can do is no limit at all. You can say that any text, there is no limit. Well, actually, there is a limit. And just to give you a ballpark, the limit is around 1 gigabyte. That's pretty long for a single string, right? So it's just on the order of magnitude. It can be very, 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 very long, okay? But it's very rare that people would actually go that far, right? So you could imagine that in such a column, you could have the entire source code of a blog post, right? If you have a blog on the internet, then typically you're using some software and it's stored in some database, very often a SQL database, and typically you would have columns in that database that contain very long strings that are a blog posts, for example. Okay. Now, I'm giving you the secret codes for use in PostgreSQL when you want to actually create attributes with these types and treat it like a restaurant menu, right? You can have the starter, the entree, the dessert, and so on. And so here, the secret codes for fixed length is char. And then you specify the length in parentheses, right? Here you say, I want exactly 10 characters. If you don't specify anything, it means 1, exactly 1 character. If you want a variable length with limit, then you use varchar. It's probably the most famous one, varchar. You see it a lot on social media and so on. So varchar 10 means a maximum of 10 characters in the string. Parenthesis, this parameter is really about the number of characters. It's not about the number of bytes, because the number of bytes could be more if you have strings with special characters like accents or other alphabets like, I don't know, Arabic, Cyrillic, Devanagari, Greek, and so on. So of course, 1 character might be more than 1 byte, right? So when we say here 10, we really mean the characters, right? Possibly complex characters. And finally, the variable length without limit. Here, it's a tad bit more complex, but actually not so complex. It's just that there is a standard and PostgreSQL doesn't follow the standard. So the standard normally, if you look at the SQL standard, it's called club. Do you know what club means? It means character large object. Club, just a club. But PostgreSQL thought that maybe that was too geeky or too complicated, and so they just call it text. So if you use PostgreSQL, club probably will not work, but just say text, and that's what it means, right? Any length. But again, if you start going beyond 1 gigabyte, then probably it will not let you go that far. Who is with me? All right, so treat it like a restaurant menu, char, varchar, and text that are going to work in PostgreSQL. And I put club in orange or in red just to emphasize that this should be the name, but PostgreSQL doesn't use that name. Yes?
You just use varchar and you anyways just want to be variable.
Instead of text? Yes, absolutely. So I didn't go into details, but if you use varchar without specifying anything, then it is a synonym for text. Right. Absolutely, but I didn't want to overload the slides too much, so the menu that I'm going to give here is not fully complete, but it's everything you need, basically. For example, if we want to go a little bit into the fun facts, char can also be called character in fully written words, And varchar can also be called, I think, character varying. And varchar is an alias, right? I just didn't want to overload my slides, so this is why I just said, char, varchar, and text without going too much in the synonyms, right? But you're absolutely right that you could also say varchar without any parameter for text. Okay? Any other questions? Yes? It is possible. So yes, maybe I can say a few words about that. Char, usually, in terms of performance, is very good because in a computer system, basically, when you have exact length, it's highly predictable in where it is in memory, and it's very efficient to then jump to the data. So char, the intuition is that it's very efficient. When you have things that vary, like character varying and text, the efficiency typically diminishes. I think I remember from the PostgreSQL documentation that PostgreSQL tends to implement primarily as text. So even the varchars would use structures that are similar to text. So there's probably not a big performance difference between varchar and text. I'm just guesstimating, right? But again, that depends on the implementation. It might be that other systems are going to do it differently. Maybe some other systems, a naive implementation of varchar is just also to just reserve the 10 characters and waste the space if it's not used, right? So you can imagine plenty of strategies. Something that's also interesting for text in PostgreSQL is that if it's very, 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 very long, then it has something called toasts that actually splits it into multiple partitions, and then it stores it in other tables. But this is all hidden from the user, right? So you see that's the beauty of data independence, is that as the user of the table, you don't need to care about these things. You just say, I want text, and that's it, right? And all the rest is magic in the background, right? So it's good to have the performance in mind, though. So if you do know that you have an exact number of characters, then it's a very good thing performance-wise to use the char type, right? Does it answer your question? Yeah? All right. Very good. So let's continue to explore the menu then. I wanted to say a few more words about strings, just so that you know. So on the left, you have various things that you can try to put in there. Of course, I'll show you later how to put the data in the table. But imagine this is what you attempt to store in the table in each one of the three scenarios. Imagine that you have char 3. Let's focus on that column right here. So if you try to put nothing, it will just put 3 spaces in there because it's exactly 3 for char. If it's less than 3 characters, again, because 3 here, it will pad the rest with spaces. So if you just say F, it's going to be F space space. Exactly 3, well, that's perfect. More than 3, error. It will not let you, right? Because this is exactly 3. However, there is an exception to that. If it's more than 3, but it's all because it's white spaces, could be spaces, tabs, new lines, or all kinds of white space characters, then it's just going to trim. So it's just going to say, okay, I'm removing all the spaces just to make it 3, right? Who is with me? Right? So you see it's exactly 3 or an error. Varchar 5 is going to just leave the string alone, but it's just going to throw an error if it's more than 5, of course, because here 5 is the max. And again, the same behavior here. If it's max 5, but it's only spaces that exceed it, then it just cuts what is needed right here. It trims. Then you have exactly 5 characters. And finally, well, text just takes whatever you give it, and that's it. Since we are people interested in advanced stuff, you know that characters have codes, right? And there is a special character that has the code 0. It's forbidden in strings, but I think not at least people who just start using the system wouldn't think of that. But just so you know, it's forbidden to have the 0 character. Right? It's anyway not a letter of the alphabet or anything, so most people don't even notice that. Okay, so this is for string. Everybody with me for strings? Okay, so let's move on to numbers. Numbers. So let's start with the easy one. So the easiest numbers that we learn in primary school are the integers, possibly negative. That's Z technically in the mathematical set. But that's the math, and the problem here is that we have machines. And as you imagine, that set is infinite, and on the machines, we cannot just store arbitrarily large integers. So we need a few tricks. And you probably already know some of these integer types from other programming languages. For whom does these do these ring a bell here? Byte short, int long. These are the Java ones. Many of you, right? Who never saw them? Oh, everybody saw them. All right, awesome. So the idea, here's the idea. Let me jump here. Yeah, the idea is that computers only understand 0 and 1, right? It's the bits. So everything must be in base 2. So internally, but of course the users don't notice, internally you have to write the number in base 2, as in shown here. And then what is typically done on the, especially on the old computers, is that we limit the number of bits you can have. For example, there is, if I go back here, for bytes, we say it's a limit of 8 bits, right? And so if you do a calculation, that gives you 256 possibilities for them, right? So that's called a byte. And actually, a byte, I think, goes from minus 128 all the way to 127, right? And that gives you exactly 256 values. That's what you can do with 8 bits. Short does the same, but all the way to 16 bits, right? Int all the way to 32 bits, and long all the way to 64 bits. And now it's pretty standard to use long everywhere, right? So speaking of them, so 8 bits, that might be not enough, so we don't have that in PostgreSQL. But 16 bits, PostgreSQL calls them small integers, right? So the small integers between 32,000 and minus 32,000 and plus 32,000. Normal integers, 32 bits. That was the standard in the 90s and maybe in the 2000s. That goes from minus 2 billion all the way to 2 billion. Who heard of the Gangnam Style video on YouTube? Some of you, right? It's the first video that broke the 32-bit integer counter because YouTube implemented the counter, the number of views, as 32-bit integers. And so Gangnam Style broke that because it went back, when you keep increasing, it gets back into the negative. And so just because of Gangnam Style, they needed to change the counter on YouTube to 64 bits. And now I think we're probably safe for a while because you would have to have 9 quintillion views in order to break that again, right? So it's probably going to be good for a few decades at least. All right, so small integers, big integers. And if you don't want to bother with the bit level, just think of them as intervals, right? These are the intervals of integers that you can use for every one of these types. And on the right, that's the size in memory, the number of bits it takes. And these are their names. So the restaurant menu, as always, small int would be for the small integers, integer would be for 32 bits, and big int, as the name indicates, would be for 64 bits. All right, everybody with me? All right. There are other synonyms, but again, I just sticked to just these 3 to not throw too much at you, right? But there are synonyms and alternate names for the same. Okay, and that I showed you. All right, but you know that not every number is an integer, and especially if you think of accounting, like a company that stores its financial records in a database, then integers are not good enough, right? So how do you store, for example, currencies and monetary amounts with Rappen, right, after the decimal point? Well, you can do that, and there are types that do exactly that. And here is how they work. You need to specify 2 things when you have a type like that. The first thing you need to specify is the precision. The precision is the total number of significant digits that you want. I gave you an example with an insane precision of 32 digits in base 10, right? I'm thinking decimal numbers here. So 32 digits, that's a lot of precision. So that's the first thing you define, a maximum precision. So it means that here, any digit beyond that would be lost. You wouldn't store them. 32 is just an example. You can pick whatever you want, right, as a value. So that's the precision, the total number of digits. And then the second thing is that we say where we put the decimal point, right? So that's why it's called fixed point decimals. Once and for all, you say the decimal point is right here. Right? And it's for every number, it's exactly right here with that many significant digits and so on. And so that's called the scale, right? You specify the number of digits after the comma, after the decimal point. That's basically, you can really see it as the location of the decimal point, if you want, right? So it means that that would be an integer, but if we move the decimal point all the way here, and now we have a decimal number with 22 digits after the comma. Who is with me? Right? Okay. So now, in PostgreSQL, what do we do? Well, first, you can do it without any limit. You can say, I want absolutely any decimal number with absolutely any precision and any scale, right? Then you just say decimal, right? Numeric is a synonym. So if you're interested in synonyms, it's also called numeric, but I just put decimal just, again, to keep it simple. So that's an example of decimal, right? As many digits as you want, and you can put the decimal point anywhere you want. But you can also restrict. And if you want to restrict, for example, you could say, I want to limit my precision to 32 digits, just 32 digits. But if you just say that, the point will be by default at the end, right? So it's going to be 32 digits and then the point. In other words, that would be integers, right? That have 32 digits. Who is with me? Right? Very good. So decimal 32 would mean all the integers with at most 32 significant digits. It's okay to have zeros at first, right? So that's why I'm saying at most 32. And finally, you can also specify a scale. So here you would say, I want a precision of 8 digits. And I want to move the decimal period by 2. So it means that I have 6 digits before the period and 2 digits after the period, right? And that's an example. You see it has 6 digits before the period and 2 digits after the period. And again, I repeat, these digits can be 0, right? So if you try to store just 159.5, that would also be fine. It would be 000.159.50. Right? Can absolutely be 0. Who is with me? Very good. Very good for money, for the financial reports and so on, for 2 digits of Rappen after the franc. Okay. And here I give you a few examples again. What happens for 3 different types? What happens if you try to put them in a table? So let's just take some time to go through them. So let's start with the first one. Just A, right? I'm hiding these 2 right here, so just this one. So this one doesn't limit anything, so pretty much anything you put in there is accepted as your decimal, right? It's fine to have, by the way, when you put it, you can have zeros in here or zeros in there. That's absolutely fine. They just get ignored then from the display. You can use the scientific notation. Remember, when you put this E, it means exponent. That means times 10 to the power of, right? So here it means minus 4,321 times 10 to the power of minus 2. What that does is just that it says there's a comma. Minus 2 means the comma is right here. It's actually 43.21, right? So it's stored as minus 43.21, right? I'm assuming most of you know the scientific notation. You also saw it on calculators. So that's decimal, just takes any number. Now, decimal 2, remember, we only specify the precision, so it means the scale is 0. So these are integers with 2 digits. So then what we do, so here it's okay, 0, 3, 3.1, that gets rounded to 3. You lose what is after the comma, because again, the scale is 0 here. Here it's 35, we lose the 1,4. Here we can't, because that would be 3,141. We can't remove digits because they're on the left of the decimal period, right? So here it's an error, right? That's not an integer that would fit in just 2 digits. And here we just store minus 43 because again, that's minus 43.21, right? So we just lose a bit of precision, but it's minus 43. Who agrees? All right. And now let's look at decimal 3.1. How many digits on the left of the decimal period here? If I say 3.1. 2 of them, exactly. 3 is the total precision. So it means I have 2 on the left and 1 on the right. 2 plus 1 equals 3. And so it means that they look like pretty much like this, right? 2 digits on the left, 1 on the right. But again, there can be zeros, right? So typically when you display it in a Jupyter notebook, it will always add a .0 if it's an integer to mark the fact that it's a scale of 1. So 0, 0.0, here we have 3.0, 3.1. Here we lose the 4. 35.1, so we lose the 4. Here we can't, because that's only 2 digits on the left alone. Here we have 4, so we can't just remove digits on the left of the decimal period. And here we have minus 43.2, and we lose the 1 in the precision, because the scale is 1. So we have only 1 digit on the right. Everybody with me? Right? So again, the way to visualize these decimal types and the precision and the scale, imagine that it's fixed. So imagine that you have placeholders for exactly the precision. So for 3.1, you have exactly 3 placeholders, 3 digits that you can hold in there. And the scale of 1 tells you where to put the decimal period in these placeholders, right? So that's pretty much it. Okay. So these are the fixed points, right? So decimal. And finally, we have something else that's called floating points. Floating points comes from the fact that it's the limitations of the fixed points. Imagine that you want to store very large numbers, like the size of the universe, or the weight of Jupiter, or the size of an atom, or the Planck constant. Do you see all the zeros that we would need for the numeric, right? Imagine 10 to the power of 37, or 10 to the power of minus 100, all the zeros that we would need to put in there. So this is why we have the floating point numbers. It basically means you don't fix the position of the decimal point. It can be anywhere, and that's specified in every value. So the way it works, it's very boring, but it's basically just a scientific notation. What you do is you write it in scientific notation, but in base 2. So you basically say that this number right here is equal to this times 2 to the power of 31. And then this 31, you encode it in here. That's the exponent. Just these bits here give you the exponent of 2. And that part right here, you encode in the blue zone, right? So that would be the bits that correspond. It's called the mantissa, right? And here, 1 bit for the sign, plus, minus, you put it in there, right? And so basically, you can take a number like that, encode it in this way in bits with the exponent of 2 right here and then the mantissa right there, and you can read it back. But when you read it back, you will lose precision because there is a limit to the number of bits that we have here. So the way to imagine these floating point numbers, it's like it's real numbers but approximated, right? So treat them like approximated real numbers. Okay. Now there are 2 standards. So it's good to standardize because if we just said that, it would be a big mess and everybody would do it in a different way, right? So if it were just that. So there are 2 standards, one on 32 bits and one on 64 bits. The standard is called IEEE 754, if you want to look it up. It's an international standard. But what you just need to retain is just roughly what it gives you. So here, if you use the 32 bits single precision standard, you roughly have 7 digits of precision. If you use the 64-bit standard, it's double that, so 15 digits of precision. And here you also have a range of powers of 10, because again, as a human, you think in powers of 10, right? So for the human being, it's roughly from minus 37 to 37, right? And here, 307. Imagine with the fixed points, the number of zeros we would need to put in there in order to do these with fixed points, right? So double precision, single precision. Single and double, again, have to do with the bits. It's a fixed number of bits here, a fixed number of bits here, sums up to 32. Fixed, sums up to 64. And since you have the exponent of 2 and the mantissa, then you can construct these numbers. Who is with me? Does anybody know what they are typically called in many programming languages like Java? Single precision, double precision. Float and double, exactly. So this one typically would be called float in many programming languages. And this one would be called double, well, exactly because of that, right? So float is on 32 bits, double is in 64 bits. But of course, it would be too simple. So in Python, that's actually not the case. In Python, float is on how many bits? In Python, it's 64. So don't be confused with the different naming conventions. You just need to look at the documentation for every language, right? So in Java, float, single precision, double for the double precision. And in Python, float gives you the double precision. And now these are the names for PostgreSQL. They are not called float and double, sadly, so that's new names to learn. They just call it real for float, just real. And then the double precision is called double precision. Right? These are the names. And the arbitrary precision is for the people who want something more customized, but you don't need to learn that because anyway, whenever you say, I want that many digits of precision, it will just fall back to the single or double precision anyway. So you can just ignore the part at the bottom and just focus on real for 32 bits, double precision for 64 bits, right? The arithmetics, when you want to compute addition, multiplication, division, and so on, of these will be very efficient because that's actually implemented on the processors of the machines. They are able to directly manipulate this, again, because it is a standard. And it is so much a standard that all the CPUs and cores in a computer know how to handle them. If you try to do addition, multiplication with the fixed points, that's going to take much more time because it involves, like in primary school, you need to put them on the sheet, align them, put the decimal periods at the right place, and so on. So that's very inefficient. But these are extremely efficient because handled directly by the hardware with the CPU registers and with the chip that is made for that. Okay, who is with me? Okay, very good. And finally, in the case of real double precision and decimal without limits, without parameters, you have three special values, which is very cool. You have minus infinity, you have plus infinity, and you have none. Do you know what none means? Anybody? Yes? Not a number, not any number, exactly. That's typically, none is typically what you get. For example, if you divide by 0, you know you cannot divide by 0. And so if you try to do that, then you get none, right? Not a number, right? So infinity, minus infinity, and none, these are just special numbers that are encoded in a specific way, can be very convenient, right? All right. So let's move on then to the others. Then we have Booleans. Booleans, super easy because there's only two of them. There is true and there is false, right? So, for example, if I say I am in Switzerland, then this is true. If I say I am in Germany, then this is false, right? So it's just first order logic, Boolean logic, and there's two of them. I don't think I need to say much, right? True, false. And you can also manipulate them, but that we'll see in the algebra later. So just two values, true and false. And the type is called Boolean. It's that simple, and there's only one. Okay, let's move on then. Then we have dates and times. Dates and times are particular for several reasons. The first reason is it's very complex, much more complex than numbers or strings and so on. It can be very complex. The second reason is that when new systems or new programming languages are invented, they are usually forgotten. Everybody remembers to offer strings and numbers and so on, but the dates and the times, they come later, right? And so, for example, in Java, for a very long time, it kept changing in every version. At some point, there was an outside third-party library, JodaTime, that gave you this, and we had to wait until Java 8 to have this then incorporated as a standard Java library. But in spite of being forgotten often or neglected, they are super important because who uses these databases? Well, every company in the world. And companies need dates and date times, of course. It's part of the daily business to save this kind of value. So this is why they are important. It's complex, but fortunately, it's a bit standardized. I'm saying a bit because it's not completely standardized. Very sadly, I wish one day everybody will handle them in the same way. This is also what makes them complex, but let's explore. I will show you. So date, time, and timestamp. a date typically in the Gregorian calendar is made of a year, a month, and a day. And here comes the first complexity. The Gregorian calendar is not the only calendar in the world. There's many others. And so you have systems that support multiple calendars. You have systems that just support the Gregorian calendar. But you see the idea, right? It's about the representation. If you think of dates in themselves, imagine very naively, you just count all of the 24 hours period since the Big Bang. It's actually just integers, right? So if you completely abstract away, a date is just an integer, right? It's the number of the day from a certain point in time. So the complexity comes from the representation, because we just don't count the date as numbers. We specify a year, a month, a day, and so on. And then in a month, there can be 32 days, 30, 31 days, 29, 28, makes the calculations also complicated. But anyway, this is the date. And as the user of the database, you can just think of it as a year, a month, and a day of the month, right? Then we have times. The times are typically made of hours, minutes, and seconds. And in SQL and in the case of PostgreSQL, you are even allowed to go all the way to microseconds. So you can have up to 6 digits after the decimal period for the seconds, right? So here too, that's a very long history, because we have what's called the sexagesimal system, because we have 60 seconds in a minute, 60 minutes in an hour, and 24 hours in a day. There has been attempts to have a decimal system for times and even for dates, but that never succeeded. So we use the sexagesimal system today, right? So as you can imagine, that also makes calculations a bit difficult, right? But again, as the user, hours, minutes, and seconds for the times. Then we have timestamps. So a timestamp has everything: the year, the month, the day, the hours, the minutes, and the seconds. Now, the purpose of a timestamp is to identify a specific point in time, right? So typically, when you give a timestamp like that, you're assuming that you have a time zone or that it's UTC and something. And then again, if you think of it, what is a timestamp? It's again just a number, right? So typically, one way that is handled is that you take January 1st, 1970 as the reference date, and then you could store it as the number of milliseconds that have elapsed since January 1st, 1970, right? This is something that is commonly done. If you want the time zone, you can also specify it. Here, you can say Central European time, right? And that would mean right here. And if you change the time zone, so when you say here, if you have another date that says 9 o'clock, so 9:31:15 GMT, that would be considered the same, right? You agree that 9:30 in the UK is the same as 10:30 right here in Zurich, right? But you can specify a time zone. It's convenient for the user that they can do that, right? Okay. So now I'm giving you the types that we can have in PostgreSQL in your table. So you can say my attribute is a date, or it's a time. You can specify the number of digits after the seconds. So 3 means that you have milliseconds as a precision. Then you have timestamps without time zone, right? Then you implicitly assume 1, probably the one where the user is. And you can specify again the precision for up 3 would be again to the milliseconds. And then you have timestamp with time zone, and 0 means it's a precision of 1 second, but no digits after the decimal periods, right? Okay, who is with me? Right, and we have a question over there. Technically, so if you want the theory of time zones, technically CET and CEST, for example, are 2 different time zones, right? We will see that they are actually encoding as an offset from GMT. So when we say CET, in fact, what we write is +01:00, right, in the literal. If you want CEST, Central European Summertime, then you say +02:00, right? Now, you can imagine that some of the libraries or some of the SQL implementation would allow you to write CET or CEST or GMT and so on. So what happens, you know, there's a bit of a myth or mythology around dates, because it's the idea, you know, you visualize when we swap to summertime or to winter time, we change the clock, you know, from 3 a.m. to 2 a.m. or 2 a.m. to 3 a.m. And then you can think of it as we lose an hour or we win an hour. But actually what it is just that you change the time zone. That's really what it means, right? So technically CEST right now still exists, right? It is a time zone, it exists. It's just that nobody is using it right now. And likewise, in 6 months, CET will be here, but nobody will actually be using it, right? Does it make sense? Yeah, all right. Very good. What can I say other than that? Oh yes, if you want fun facts. So there are 2 time zones that are kind of standard. So there is GMT and UTC. Does anybody know the difference between GMT and UTC? So GMT is basically based on the rotation of the Earth. So the start, I have 5 minutes until the break, so I can spend them explaining this. The origin of the time zones actually has to do with trains and the development of the railway systems. Before the trains, before the railway, nobody really cared that the times were not exactly the same ones in different cities, right? So every city was kind of on their own time. But the problem with the trains is that they moved so fast from city to city, you needed a reliable schedule and to say at what time they arrive and so on. And so we needed to synchronize across cities to be on the same time. But then you quickly run into issues of that mathematicians would call differential geometries and manifolds that have holes and so on. But basically, you cannot. It would be tough to have a single time over the entire planet, right? So that's where the system breaks. And so the idea at that time was to just say, okay, then we cut the world in 24 zones, right? It's 360, we divide it in 24. And then we just agree that within each one of these zones, we are on the same time. Then when we switch the zone, you just have 1 hour of difference, right? In some cases, half an hour or a quarter of hour. We just need to standardize it because it's just a standard. Then there was a funny fight between the French and the British on where the standard time should be. In the end, it's Greenwich that was selected, and GMT is this Greenwich mean time. That is the reference for the times. That's based on the rotation of the Earth. So you have to look at the stars and the sun and so on. UTC is based on the atomic clock. It's the definition of a second based on the quartz, and I'm not sure if it's even the quartz that's defined it in the international system. I forgot, but there is a precise definition. What happens is that the rotation of the Earth is in fact not exactly 86,400 seconds. It actually even fluctuates. It's not every day the same. And it even slows down on the very long term because the Earth rotation is slowly slowing down. And so the consequence of that is that UTC and GMT, they kind of deviate from each other. And so this is why every year you might hear an announcement that a leap second was added or not added. And that's because we try to synchronize UTC and GMT and keep them close to each other, right? So UTC, the atomic clock, GMT is the rotation of the Earth, right? Last piece of trivia, it seems that recently the Earth has actually been accelerating again, so we might not have a leap second, but the opposite of that. So that's a bit of suspense on what's going to happen, maybe at the end of this year or the following year. All right, so I just used the 5 minutes to the break to tell the fun stories. Then I will get back to this. I'll see you in 15 minutes at 15 past 11 for the continuation. Thank you.